Okay, welcome back. This is now part 2 of rules of replacement. Should write that down, part 2. So we've been talking about the rules of replacement in the system SD+, and we've covered a few of them. Actually, let me see where. There we go. So we've covered some of these somewhat briefly, and we've done a proof of a few of these. And we've shown some examples of how we would have derived them in the regular system SD. So let me talk a little bit about the De Morgan rules. And we've already shown that these are symmetrically equivalent, but let me actually go through and let's go over an example of one of these and see why these rules of replacement are valid. So let me do this one, and I'll try to actually go through the more difficult direction. And again, like I said before, I encourage you to go over these yourself and try to actually derive them for yourself. So let's look at this direction. We're going to go from not P or not Q to saying not P and Q. And it helps to think about this intuitively first. So think about what this is saying. This is saying, look, either not P is the case or not Q is the case, where the or here is inclusive. So it might be that both of them are not the case, right? That it's not P and it's also not Q. We're just saying, for this whole sentence to be true, at least one of them has to not be the case. What this is saying here is it's not the case that both P and Q are true. That's equivalent to just saying, look, at least one of them has to be false, maybe both of them. This sentence is saying, look, not both of them are true. Maybe both of them are false, but definitely not both of them are true. So that's using our semantic intuition to see why these two are equivalent. But we can also prove this. We can also sort of derive them in our system. So suppose we have, for example, a sentence. We have not A or not B. And my goal is to get not A and B. This is my goal. Now there's two different ways we could actually go down this route. And one of them is to think, look, since there's a negation out front here, maybe what we should do is do a negation introduction, and so assume A and B. Alternatively, we might use disjunction elimination, right? We might do a kind of like proof by cases. So we assume that not A is the case, and then try to derive not A and B, or we try to, and then we assume not B is the case, and then again derive this. And to be honest with you, I'm not quite sure which one is easier. So let me try, we'll do disjunction elimination, because I think people need to see that one a little bit more to get familiar with it. So let's assume not A in one case, and in the other case we're going to assume not B. And our goal, so this is going to be, we're going to get this by disjunction elimination, citing line 1, and then our two subderivations. And our goal in each of these is going to be not A and B. Not A and, oh, it's not a very good A. There we go. Okay. So, and actually, now that I wrote this out, I realize that this is probably going to take us a longer way, but that's okay. This will be informative. So, my goal here is to get not A and B, and to do that, I'm going to use negation introduction to try to get that. So I'm going to assume A and B, and I'm going to do that for the purposes of negation introduction. And I was a little bit lazy up here, but this up here should say for the purposes of disjunction elimination. Okay, so my goal here in this subderivation is, if I want to get negation introduction is to get a contradiction. And if we look, we notice that we could actually get this relatively quickly. We have not A at our disposal here in there, because this scope line is still open to us in here. So I can write down not A by reiteration from line 2. I didn't write line 2 yet here. No, sorry. And we can actually then also get A by disjunction elimination from line 3. And now we have the contradiction. We have a contradiction, which means we can introduce a negation to the claim that we assumed with. So line 6 will be negation introduction, setting line 3 to 5. Okay, and so now we're done with this subderivation. Now we actually just have to do it again down here. So we're going to use the same strategy. We're going to say, okay, since we have a negation out front, we're going to assume the opposite. So we're going to assume A and B. And we're going to try to derive a contradiction. So we're assuming this for the purposes of negation introduction. And our goal now is going to be a contradiction. And hopefully you'll see that we're going to actually just use the same strategy that we did up here. Namely, we notice that not B is accessible to us, right? Nothing up in this subderivation is, because it's now closed off to us. But not B, this is accessible to us. So we can write down not B by reiteration from line 7. This is line 7. And we can then use conjunction elimination. Hopefully I didn't misspeak earlier about that. So we have B by conjunction elimination. And now we have the contradiction that we were looking for. So now we can use negation introduction to get not A and B. And now this subderivation is completed as well, which means we've completed a proof, right? Because we were going to use disjunction elimination, assume that not A is the case, show that that leads to not A and B, assume that not B is the case, derive not A and B, and then we can use the rule of disjunction elimination to justify this final claim then in our main scope line. So here we would cite lines 2 through 6 and 7 through 11. Okay, so what I've just done is gone from this direction. I've assumed not A or not B and derived not A and B. What this rule of replacement, and this one's called, both of these are called De Morgan's laws. De Morgan's laws just let us replace one with the other. So the De Morgan's law says, look, you know what, I'll make it easier for you. Don't have to worry about that. You can go straight from this to this, or vice versa, right? So if we had not A and B, we could then have, by De Morgan's law, we could say, okay, not A or not B. And you would say DM is usually the short. I think the book uses, they use DEM, but I'm happy if you use just DM. That's okay. You can just cite that if this were line 1. You can just, by De Morgan's law, on line 1. Okay, so that's for De Morgan law, and similarly, this holds for the disjunction, the case of the disjunction as well. So if we have not P or Q, you can actually then derive not P and not Q, and vice versa, right? So you can always go back and forth. You can replace, whenever you have a sentence of this form, you can always replace it with this form. And again, it deserves repeating that P and Q here are not necessarily atomic sentences. They might be complex sentences. So P might be some really complicated conjunction, but that's okay. If on the outside you have this form, then you can actually turn it and you can replace it into a sentence that has this form. Okay, so let's talk about a few of these others. So I think what we have left is here transposition, and we have exportation, distribution, and equivalence. You'll notice in the case of distribution that we actually just did this one. So this was actually a quiz question. We had, I asked you to derive or show that these two are equivalent. So you got to assume P and Q are R, and you had to derive P and Q or P and R. And in the case, this was, I think, question 3 on quiz 6. So what you had to do was assume this side, derive the right, and then assume the right side in a separate derivation, and then derive the left. And this will also hold for the disjunction. So if you didn't get a chance to or if you aren't confident that you actually got this question and you're watching this video before you got the quiz back, I would recommend that you actually check for yourself that this equivalence holds as well. And we'll maybe go through this in Monday's class. And okay, so let me actually just do a little bit, let me talk about transposition. And this is sometimes also known as contraposition. So the rule says, look, whenever you have a sentence of this form, this conditional, you can swap the order of the antecedent and the consequent and take the negation of both. In other words, you can say, look, if I have if P then Q, that's just as well as me saying not Q, if not Q, then not P. So let's prove to ourselves that this is in fact a valid rule. And let's go with orange. So I'm going to assume in this first case that I have if P then Q. And my goal here is going to be not Q then not P. This is my goal. Now, the strategy, as always, when you ever have a goal that has a conditional, before you even look up here, before you even look up there, immediately just start expanding and unpacking the goal sentence. And since this is a conditional, we're going to use the conditional introduction. And to do conditional introduction, you have to assume as your antecedent, your antecedent becomes the auxiliary assumption, so in this case not Q, and the consequent is the last line in your subderivation. And so this, when we're completed, will be by conditional introduction. Okay, so now our subgoal now is to get not P. And the way we have to do this is try to actually find a way to introduce this negation. And the best strategy in our case is going to assume P for the purposes of negation introduction. Right, so this is why we're making this assumption. And we can write this down here as well. So once we have this derivation, we'll be able to have negation introduction. We'll be able to use negation introduction to get not P. Our goal then in this subderivation is to get a contradiction. And if we look, we'll notice that we have not Q, and we also have Q. So that's a good candidate for finding a contradiction. Moreover, we'll notice that we have this conditional here, if P then Q, and we also have P, which is the antecedent of that conditional. And as we know, whenever we have a sentence where we have a conditional, and we also have the antecedent of that conditional, then we can actually take out, by conditional elimination, we can take out the consequent. So then, let's do that. We can get Q, and the way we can get Q is by using conditional elimination, citing line 3, and line 1, right? We have if P then Q, and we also have P. So now we can actually derive Q. And then now this is a fairly simple step. We can just reiterate not Q from line 2. And now we have the contradiction that we want. So we can actually introduce the negation. Right? So because we assumed P and P led us to a contradiction, we can then derive not P. And so this will be from line 3 to 5. And then we're done. We just need to finish the citation for this last line. So we assumed not Q, we were able to derive not P, so that means we can introduce this conditional. Now if not P, then not, if not Q, sorry, then not P. And this will be citing from lines 2 through 6. Okay, so that is transposition, and we can also prove the other direction, and I encourage you to do that. There's actually also, we've seen exportation already as one of the homework questions. So we asked you, I can't remember which order, but I definitely know there was one question where you got to assume one and you had to show that you could derive the other. And in fact, I think we even showed that these two were equivalent in the problem sets. So you had to be able to derive one from the other. So the only thing then that we're left with are these equivalences. And I'm going to stop our video here, but talk a little bit more about this equivalence replacement rule and actually improve these for ourselves as well. So up to now, we've covered just about all of these rules in some form or another, either hinted at a place where we've done them in one of the problem sets already, or I've actually gone ahead and done at least one of the derivations for an instance of one of these rules, just to prove to ourselves that they are in fact derivable in our old system SD. So I'll see you in the next video.